let's look a little deeper into the ortho-para directing group. So you might remember from the video where we created that large table. These are the directing groups that have non-bonding electrons on the atom directly bonded to the ring. Non-bonding electrons on atom directly bonded to ring. Or an alkyl group. And these are all electron donating groups. Or EDGs. So when we have an electron donating group, that ends up stabilizing the carbocation intermediate only when we do ortho-para substitution. So if we remember the two electrophilic aromatic substitution reactions that we've talked about so far, halogenation and nitration, one of the steps is forming that carbocation intermediate that is not aromatic. That is the highest energy intermediate that ends up being the rate determining step. And so if we can lower the energy of that carbocation intermediate, the reaction happens quicker and we get a more stable intermediate. So that happens when we have electron donating groups. So we'll write here, stabilizes the carbocation intermediate during ortho-para substitution. So let's look at para bonding, for example. And we'll add an electron donating group, an ortho-para directing group to the ring. You could pick any. I just picked a methoxy group. And let's say this is our starting material and we want to know what happens if we add an electrophile, if we do electrophilic aromatic substitution. So we'll just keep E+ as the electrophile. Just a generic electrophile. So if any electrophile is being added, we're adding to the para position, so opposite of the methoxy group. Electrons from the pi bond will create a bond to the electrophile. It bonds opposite, so it'll bond right here, opposite in the para position. We're writing that because that's what we're looking at here, para bonding. Don't forget we have a hydrogen here. And because we broke that pi bond, we now have a carbocation at that carbon. Now this is where those electrons on the methoxy group become important. Once we generate this carbocation intermediate, we can actually see that we can stabilize the intermediate by using these non-bonding electrons. They can create a double bond between the oxygen and the carbon in the ring, and then we can shift over a pi bond to fill the shell of that carbocation. So if we're drawing resonance structures here, we can see that we now have no open shell carbon, and we do have a positively charged oxygen. Let me put these electrons at the bottom. We have a positively charged oxygen, but it's still closed shell. So overall, this is a more stable resonance contributor than the carbocation structure that we drew to the left. There are other possible resonance structures, but this is really the important one that explains why having an electron donating group results in orthopara products and is an activating substituent. So this intermediate, let's write some of that information down. This intermediate is a more stable resonance contributor. Because all atoms are closed shell, and so that means that less energy is required to get to this carbocation intermediate. Now, I'll only draw out the para bonding structures, but a similar intermediate, a similar resonance contributor is possible when you do ortho bonding, and that's why this is an orthopara director. You can certainly try that out and make sure that is the case. Now let's look at meta bonding and why these electron donating groups are not meta directors. So we'll start with the same starting material, methoxybenzene. And let's say we're adding an electrophile to the meta position. So that's one carbon away. One carbon away from the methoxy group. Now, if we draw out this structure where we add the electrophile at the meta position, to remember we have a hydrogen, and that generates a carbocation at the carbon adjacent to the methoxy group. Now let's think about possible resonance structures. So we could fill the shell of that carbocation by shifting over the pi bond there. Now we have a carbocation at the top here. We could do the same thing shift a pi bond over to move the carbocation to another carbon around the ring, but there's really no way for the electrons on the oxygen to then be donated into the ring. Let me erase this arrow real quick. Just say hypothetically, so I'll use green here, if we add electrons to create a double bond there, then we need to move these electrons away somewhere, but they can't create a pi bond here because we have an sp3 carbon where the electrophile and the hydrogen are. And you could say the same thing for the first structure. So there's no way for those electrons to be donated into the ring. So really the only possibilities are kind of just shifting around where the carbocation is. Which is exactly what we drew when we first wrote out these reactions, where we're just working with plain benzene. That benzene carbocation can resonate around the ring, but having this electron donating group doesn't make it any more stable when we are bonding at the meta position specifically. So that's why these types of substituents are not meta-directors, they're only ortho-para directors. And let's just quickly look at these two possible locations of bonding on a reaction coordinate diagram. Reaction coordinate diagram. Remember, the y-axis for a reaction coordinate diagram is energy, Gibbs free energy. The x-axis is reaction progress. And in both cases, we start with the same energy of reactants. We have our electron donating group. We're adding the same electrophile in both cases. We saw from resonance structures that when we form the carbocation intermediate for ortho-para, that carbocation is stabilized, so it's at a lower energy than when we do meta substitution. So our intermediate is lower energy. That also means that we can reach that intermediate with less energy, so a lower activation energy. And that's really what makes this a faster reaction, is that we have a lower activation barrier to overcome. So while it might be possible to get some meta products when you have an electron donating group bonded to a benzene ring, most of the reagents are going to form the ortho or para products first because that's a faster reaction, so the reagents will be used up making that intermediate before the meta substitution intermediate.